The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, shall we start? Okay, so the main job of today is eigenvalues and eigenvectors. The next section in the book, and a very big topic, and things to say about it. I do want to begin with a recap of what I didn't quite finish last time. So what we did was solve this very straightforward equation, straightforward except that it has a point source, a delta function. And we solved it both the fixed case when a straight line went up and back down, and in the free fixed case when it was a horizontal line and then down with slope -1. And looking, there are different ways to get to this answer. But once you have it, you can look at it and say, well, is it right? Certainly the boundary conditions are correct. Zero slope, went through 0, that's good. And then the only thing you really have to check is, does the slope drop by 1 at the point of the impulse? Because that's what this is forcing us to do. It's saying the slope should drop by 1. And here the slope is 1 minus a going up. And if I take the derivative, it's minus a going down. 1 minus a dropped to minus a, good. Here the slope was 0. Here the slope was -1, good. Okay, so those are the right answers, and this is a simple but really great example. And then what I wanted to do was catch the same thing for the matrices. So those matrices, we all know what K is and what T is. So I'm really solving K inverse equal identity. That's the equation I'm solving. So I'm looking for K inverse and trying to get the columns of the identity. And you realize the columns of the identity are just like delta vectors. They've got a 1 in one spot. They're a point load, just like this thing. Okay, so can I just say how I remember K inverse? I finally, again, there are different ways to get to it. One way is MATLAB, just do it. But I guess maybe the whole point of these and the eigenvalues that are coming to is this, that we have here the chance to see important special cases that work out. Normally, we don't find the inverse, print out the inverse of a matrix. It's not nice. Normally, we just let Eig find the eigenvalues, because that's an even worse calculation, to find eigenvalues in general. I'm talking here about our matrices of all sizes, n by n. Nobody finds the eigenvalues by hand of n by n matrices. But these have terrific eigenvalues and especially eigenvectors. So in a way, this is a little bit like typical of math, that you ask about general stuff where you write the equation with a matrix A. And so that's the general information. And then there's the specific, special guys with special functions. And here there'll be sines and cosines and exponentials. Other places in applied math, they're Bessel functions and Legendre functions, special guys. So here, these are special then. And how do I complete K inverse? So this 4, 3, 2, 1. Well, let me complete T inverse. You probably know T inverse already. So this is 4, 3, 2, 1 is when the load is way over at the far left and it's just descending. And now I'm going to, let me show you how I write it in. So I pay attention here to the diagonal. So this will be 3, 3, 2, 1. Do you see that that's the solution that's sort of like this one. That's the second column of the inverse, so it's solving, I'm solving t inverse equal I here. It's the second column is the guy with a 1 in the second place. So that's where the load is in position number 2. So I'm level 3, 3 up to that load, and then I'm dropping after the load. Okay, what's the third column of T inverse? So the third column, I started with that first column, and I knew that the answer would be symmetric because T is symmetric, so that allowed me to write the first row, and now we can fill in the rest. So what do you think if the point load is now, I'm looking at the third column of the identity, the load is moved down to position number 3. So what do I have there and there? 2 and 2. And what do I have last? 1. It's dropping to 0. You could put 0 in green here if you wanted. 0 is the unseen last boundary, a row at this end. Okay, and finally, what's happening here? What do I get from that? All 1, 1, 1 to the diagonal, and then, sure enough, it drops to 0. So this would be a case where the load is there. It would be 1, 1, 1, 1, and then boom. No, it wouldn't be. It would be more like this. 1, 1, 1, 1, and then down to 0. Okay. That's a pretty clean inverse. That's a very beautiful matrix. Don't you admire that matrix? I mean, if they were all like that, gee, this would be a great world. But of course, it's not sparse. And you have to face, that's why we don't often use the inverse. Because we had a sparse matrix T that was really fast to compute with. And here, if you tell me the inverse, you've actually slowed me down because you've given me now a dense matrix, no zeros even, and multiplying T inverse times the right side would be slower than just doing elimination. Okay, now this is the kind of more interesting one, because this is the one that has to go up to the diagonal and then down. So can I fill in what I think the way this one goes? I'm going upwards to the diagonal, and then I'm coming down to 0. Remember that I'm coming down to 0 on this K. So 0, 0, 0, 0 is kind of the row number. If that's row number 0, here's 1, 2, 3, 4, the real things, and then row 5 is getting back to 0 again. Okay. So what do you think? Finish the rest of that column. So you're telling me now the response to the load in position 2. So it's going to look like this. In fact, it's going to look very like this. It'll be, there's the 3, and then this is in position 2, and then I'm going to have something here and something here, and it'll drop to 0. What do I get? 4, 2. 6, 4, 2, 0. Dropping to 0. Okay, I'm going to finish this in, but then I'm going to look back and see have I really got it right. Okay, how does this go now? Let's see. Now it's going up from 0 to 2 to 4 to 6. That's on the diagonal. Now it starts down. It's got to get to 0, so that'll be a 3. Here's a 1 going up, 2 to 3 to 4, is that right? And then drop fast to 0. Is that correct? Think so, yep. Except Wait a minute now. Okay, we've got the right overall picture. Climbing up, dropping down. Climbing up, dropping down. Climbing up, dropping down. All good. But we haven't checked yet that the change in the slope is supposed to be 1. And it's not. Here the slope is like 3. It's going up by 3s, and then it's going down by 2s. So we've gone from going up at a slope of 3 to down to a slope of 2, like up 3, down, just like this, but that would be a change in slope of 5. Therefore, there's a 1/5. So this is going up with a slope of 4 and down with a slope of 1. 4 dropping to 1 when I divide by the 5. That's what I like. Here's up by 2s, down by 3s. Again, it's a change of 5, so I need the 5. Up by 1s, down by 4. That's a fast drop of 4. Again, the slope changed by 5, dividing by 5. That's got it. So that's my picture. You could now create K inverse for any size. And more than that, sort of see into K inverse what those numbers are. Because if I wrote the 5 by 5 or 6 by 6 without doing it a column at a time, it would look like a bunch of numbers. But you see it now. Do you see the pattern? Right. Okay. So that's what this is one way to get to those inverses, and homework problems are offering other ways. T in particular is quite easy to invert. Okay. Do I have any other comment on inverses before the lecture on eigenvalues really starts? Maybe I do have one comment, one important comment. It's this, and I won't develop it in full, but let's just say it. What if the load is not a delta function? What if I have other loads, like the uniform load of all 1s or any other load? What if the discrete load here is not a delta vector, I now know the response, here's the way. I now know the responses to each column of the identity, right? If I put a load in position 1, there's the response. If I put a load in position 2, there's the response. Now, what if I have other loads? Let me take a typical load. What if the load was, well, the one we looked at before. If the load was 1, 1, 1, 1, so that I had the bar was hanging by its own weight, let's say. So, in other words, could I solve all problems by knowing these answers? That's what I'm trying to get to. If I know these special delta loads, then can I get the solution for every load? Yes, no. What do you think? Yes. Right. Okay. Now, with this matrix, it's kind of easy to see, because if you know the inverse matrix, well, you're obviously in business. If I had another load, say another load F for load, I would just multiply by K inverse. No problem. But I want to look a little deeper, because if I had other loads here than a delta function, if I had 2 delta functions, I could just combine the 2 solutions. That's linearity that we're using all the time. If I had 10 delta functions, I could combine them. But then suppose I had instead of a bunch of spikes, instead of a bunch of point loads, I had a distributed load, like all 1s. How could I do it? Okay, main point is I could, right? If I know these answers, I know all answers. If I know the response to a load at each point, then, okay, come back to the discrete one. What would be the answer if the load was 1, 1, 1, 1? Suppose Suppose I now tried to solve the equation KU equal ones of 4. Ones of 4 and 1. So all ones. What would be the answer? How would I get it? I would just add the columns. Now, why would I do that? Right, because this, the right-hand side, the input, is the sum of the 4 columns, the 4 special inputs. So the output is the sum of the 4 outputs. Right. In other words, as you saw, we must know everything, and that's the way we really know it. By linearity, if the input is a combination of these, the output is the same combination of those. Right. So, for example, in this T case, if the input was, if I did TU equal that ones, I would just add those, and the output would be 10, 9, 7, 4. That would be the output from 1, 1, 1, 1. And now, oh boy, yeah, I may, actually, let me just introduce a guy's name for these solutions, and not today show you, you have the idea, of course. Here we added, because everything was discrete. So you know what we're going to do over here. We'll take integrals, right? If a general load will be an integral over point loads. That's the idea, a fundamental idea, that some other load, f of x, is an integral of these guys, so that the solution will be the same integral of these guys. Let me not go there except to tell you the name, because it's a very famous name. This solution U with the delta function is called the Green's function. So I've now introduced the idea, this is the Green's function. This guy is the Green's function for the fixed problem. And this guy is the Green's function for the free fixed problem. And the whole point is, maybe this is the one point I want you to sort of see, always by analogy. The Green's function is just like the inverse. Knowing the Green's function is, what is the Green's function? The Green's function is the response at x to the u at x when the impulse is at A. So it sort of depends on two things. It depends on the position A of the input, and it tells you the response at position X. So the Green's function has, and often we would use the letter G for green. Okay, so it depends on X and A. And maybe I'm happy if you just sort of see, yeah, in some way, what we did there is just like what we did here, and therefore the Green's function must be just the differential continuous version of an inverse matrix. Let's move on to eigenvalues with that point sort of made but not driven home by many examples. Okay. Question. I'll take a question though. Sure.
Yeah, I just have a question.
Yeah.
Intuitively, why does the second row / column of the inverses over there represent the slope of the functions that we have graphed? Because we were talking about earlier, like how you're obviously increasing.
Yeah. Why did I increase 0, 3, 6 and then decrease 6?
Why does that make sense?
Well, it's intuitively it's because this is copying this. What's wonderful is that it's a perfect copy. I mean, intuitively, the solution to our difference equation should be like the solution to our differential equation. That's why if we have some computation of some differential equation that we can't solve, which would be much more typical than this one, that we couldn't solve it exactly by pencil and paper, we would replace derivatives by differences and go over here, and we would hope that they were like, pretty close.
So does that mean
Here they're right, they're the same, yeah.
does that mean each of the other columns have like physical meaning as well?
Oh, the other columns, absolutely. These guys? Yeah. 0, 2, 4, 6 going up. 6, 3, 0 coming back. Yeah. So that's a discrete thing of one like that. And then the next guy and the last guy would be going up 1, 2, 3, 4, and then sudden drop. Yeah. So that was. Thanks for all questions. I mean, this sort of, by adding these guys in, the first one actually went up that way. You see the Green's functions, but of course this has a Green's function for every A. And X and A are running all the way from 0 to 1. Here, they're just discrete positions. Thanks. Other points, yeah. So playing with these delta functions and coming up with this solution, well, as I say, different ways to do it. I worked through one way in class last time. It takes practice. So that's what the homework's really for, is, you can see me come up with this thing, then you can, with leisure, you can follow those steps, but you got to do it yourself to see. Okay, eigenvalues. And, of course, eigenvectors. We have to give them a fair shot here. Okay. All right, square matrix. Now, so I'm talking about general, what eigenvectors and eigenvalues are and why do we want them. I'm always trying to say, what's the purpose? I'm not doing this just for abstract linear algebra. We do this, we look for these things because they tremendously simplify a problem if we can find them. So, what's an eigenvector? The eigenvalue is this number, lambda, and the eigenvector is this vector y. And now, how do I think about those? Well, suppose I take a vector, and I multiply by a. So the vector's headed off in some direction. Okay. There's a vector v. If I multiply, and I'm given this matrix, so I'm given the matrix, whatever my matrix is. Could be one of those matrices, any other matrix. If I multiply that by v, I get some result, av. Okay, what do I do? I look at that and I say that v was not an eigenvector. Eigenvectors are the special vectors which come out in the same direction. AV comes out parallel to V. So this was not an eigenvector. Very few vectors are eigenvectors. They're very special. Most vectors, that'll be a typical picture. But there's a few of them where I have a vector y, and I multiply by a, and then what's the point? AY is in the same direction. It's on that same line as y. It could be, it might be twice as far out. That would be AY equal 2y. It might go backwards. This would be a possibility AY equal minus y. It could be just halfway. It could be not move at all. That's even a possibility. AY equals 0y. Count that. Those y's are eigenvectors, and the eigenvalue is just, from this point of view, the eigenvalue is coming second because so y was a special vector that kept its direction, and then lambda is just the number, the 2, the 0, the minus 1, the 1/2, that tells you stretching, shrinking, reversing, whatever. That's the number, but y is the vector. And notice that if I knew y, and I knew it was an eigenvector, then of course if I multiply by A, I'll learn the eigenvalue. And if I knew an eigenvalue, you'll see how I could find the eigenvector. Problem is, you have to find them both, and they multiply each other. So we're not talking about linear equations anymore, because one unknown is multiplying another. But we'll find a way to look to discover eigenvectors and eigenvalues. You see now here's, I said I would try to make clear what's the purpose. The purpose is that in this direction, on this y line of multiples of y, A is just acting like a number. A is some big n by n, 1,000 by 1,000 matrix. So 1,000,000 numbers. But on this line, if we find it, if we find an eigen line, you could say, an eigen direction, in that direction, A, all the complications of A are gone. It's just acting like a number. So in particular, we could solve 1,000 differential equations with 1,000 unknown u's, with this 1,000 by 1,000 matrix. We could find a solution. We can find a solution, and this is where the eigenvector and eigenvalue are going to pay off. For this, you recognize this matrix A is of size 1,000. So this is, and U is a vector of 1,000 unknowns. So that's a system of 1,000 equations. But if we have found an eigenvector and its eigenvalue, then the equation will, if it starts in that direction, it'll stay in that direction. And the matrix will just be acting like a number. And we know how to solve U prime equal lambda U, right? That one-by-one scalar problem, we know how to solve. The solution to that is e to the lambda t. And, of course, it could have a constant in it. Don't forget that these equations are linear. If I take 2 e to the lambda t, I have a 2 here and a 2 here, and it's just as good. So I better allow that as well. A constant times e to the lambda t times y. Notice this is a vector. It's a number times a number, the growth. So the lambda is now, for the differential equation, the lambda, this number lambda is crucial. It's telling us whether the solution grows, whether it decays, whether it oscillates. And we're just looking at this one normal mode, you could say normal mode for eigenvector, y. We certainly have not found all possible solutions. But this is, we found, if we have an eigenvector, we found that one. Okay. Well, so, and just other uses, and then let me think. Other uses, what? So let me write again the fundamental equation, a y equal lambda y. Suppose, so that was a differential equation. Going forward in time. Now, if we go forward in steps, we might multiply by a at every step. So tell me an eigenvector of a squared. I'm looking for a vector that doesn't change direction when I multiply twice by a. You're going to tell me it's y. Y will work. If I multiply once by a, I get lambda times y. When I multiply again by a, I get lambda squared times y. You see, eigenvalues are great for powers of a matrix, for differential equations. The nth power will just take the eigenvalue to the nth power of a will just have lambda to the nth there. You know, the pivots of a matrix are all messed up when I square it. I can't see what's happening with the pivots. The eigenvalues are a different way to look at a matrix. The pivots are critical numbers for steady state problems. The eigenvalues are the critical numbers for moving problems, dynamic problems. Things are oscillating or growing or decaying. Okay, and by the way, let's just recognize, since this is the thing that's changing in time, what would be the, I'll just go down here, e to the lambda t, let's just look and see. When would I have decay, which you might want to call stability, a stable problem? What would be the condition on lambda to get for this to decay? Lambda less than 0. Now, there's one little bit of bad news. Lambda could be complex. Lambda could be 3 plus 4i. It can be a complex number, these eigenvalues, even if a is real. Oh, you'll say, how did that happen? Let me see. I better think. Well, let me finish this thought. Suppose lambda was 3 plus 4i. What would it then, so I'm thinking about what would e to the lambda t do in that case? So this is a small example. If I had lambdas 3 plus 4i t, what does that do as time grows? It's going to grow and oscillate. And what decides the growth? The real part. So it's really the decay or growth is decided by the real part, the 3, e to the 3t, that would be a growth. So let me put growth, and that would be, of course, unstable. And that's a problem when I have a real part of lambda bigger than 0. And then if lambda has a 0 real part, so it's pure oscillation, let me just take a case like that. So e to the 4it, so that would be oscillating, right? Yeah, it's cos 4t plus I sine 4t, it's just oscillating. Okay. All right, so in this discussion we've seen growth and decay. Oh, tell me the parallels, because I'm always shooting for the parallels. What about the growth of A? What matrices? Yeah. How can I recognize a matrix whose powers grow? How can I recognize a matrix whose powers go to 0? So that would be I'm asking you for powers here, over there for exponentials somehow. So here would be A to higher and higher powers goes to 0, the 0 matrix. In other words, when I multiply by that matrix, I get smaller and smaller and smaller matrices, 0 in the limit. What do you think's the test on the lambdas now? So what are the eigenvalues of A to the k? Let's see, if A had eigenvalues lambda, A squared will have eigenvalues lambda squared, A cubed will have eigenvalues lambda cubed, A to the 1000th will have eigenvalues lambda to the 1000th. And what's the test for that to be getting small? Lambda less than 1. So the test for stability will be, in the discrete case, it won't be the real part of lambda, it'll be the size of lambda less than 1. And growth would be the size of lambda greater than 1. Yeah, so, and again, there'll be this borderline case when the eigenvalue has magnitude exactly 1. Okay, so you're seeing here and also here the idea that we may have to deal with complex numbers here. We don't have to deal with the whole world of complex functions and everything, but it's possible for complex numbers to come in. Well, while I'm saying that, why don't I give an example where it would come in? suppose so this is this is going to be a real matrix with complex eigenvalues, complex lambdas. Okay, it'll be an example. And okay. So I guess I'm looking for a matrix where y and ay never come out in the same direction. For real y's, I know, okay, here's a good matrix. Take the matrix that rotates every vector by 90 degrees. Or by theta, but let's say, here's a matrix that rotates every vector by 90 degrees. I'm going to raise this board and hide it behind there in a minute. I just wanted to open up this thought that we will have to face complex numbers. You probably have, if you know how to multiply two complex numbers and add them, you're okay. This isn't going to turn into a big deal. But let's just realize that suppose that matrix, if I put in a vector y and I multiply by that matrix, it'll turn it through 90 degrees. So y couldn't be an eigenvector. That's the point I'm trying to make. No real vector could be the eigenvector of a rotation matrix because every vector gets turned. So that's an example where you'd have to go to complex vectors. And I think if I tried the vector 1i, so I'm letting the square root of -1 into here, then I think it would come out. Let's see, if I do that multiplication, I get -i, and I get 1, and I think that this is, what is it? This is probably -i times that. So this is -i times the input. No big deal. That was like, you can forget that. It's just complex numbers can come in. Right. Okay. Okay. Now let me come back to the main point about eigenvectors. Okay. Okay. All right. So things can be complex. All right. So the main point is, how do we use them? And how many are there? Well, here's the key. That a typical good matrix, which includes every symmetric matrix, so it includes all of our examples and more, if it's of size 1,000, it will have 1,000 different eigenvectors. And let me just say, for our symmetric matrices, those eigenvectors will all be real. They're great, the eigenvectors of symmetric matrices. Oh, let me find them for one particular symmetric matrix. Say this guy. So that's a matrix, 2 by 2. How many eigenvectors am I now looking for? 2. You could say, how do I find them? Maybe with that 2 by 2, I can even just like wing it. We can come up with a vector that is an eigenvector. That's what we're going to do here. Is we're going to guess the eigenvectors, and then we're going to show that they really are eigenvectors, and we'll know the eigenvalues, and it's fantastic. So let's start here with the 2 by 2 case. Anybody spot an eigenvector? Is 1, 0 an eigenvector? Try 1, 0. What comes out of 1, 0? Well, that picks the first column, right? That's how I see multiplying by 1, 0. That says take one of the first column. And is it an eigenvector? Yes, no? No. This vector is not in the same direction as that one. No good. Okay. Now, can you tell me one that is? You're going to guess it. 1, 1. Try 1, 1. Do the multiplication, and what do you get? Right? What do I get from, if I input this vector y, what do I get out? Actually, I get y itself. Right? So I get, the point is it didn't change direction, and it didn't even change length. So what's the eigenvalue for that? So I've got one eigenvalue now, one eigenvector, 1, 1, and I've got the eigenvalue. So here are the vectors, the y's, and here are the lambdas, and I've got one of them, and it's 1, right? Would you like to guess the other one? I'm only looking for 2 because it's a 2 by 2 matrix. So let me erase here. Hope that you'll come up with another one. 1, -1 is certainly worth a try. Let's test it. If it's an eigenvector, then it should come out in the same direction. What do I get when I do that? If I do that multiplication, 3, and I get 3 and minus 3. So have we got an eigenvector? Yep. And what's, so if this was y, what is this vector? 3y. So there's the other eigenvector is 1 minus 1, and the other eigenvalue is 3. Okay. So we did it by spotting it here. That's, MATLAB can't do it that way. It's got to figure it out. But we're ahead of MATLAB this time. Okay. All right. So what do I notice? What do I notice? What do I notice about this matrix? It was symmetric. And what do I notice about the eigenvectors? If I show you those two vectors, 1, 1, and 1 minus 1, what do you see there? They're orthogonal. 1, 1 is orthogonal to 1 minus. Perpendicular is the same as orthogonal. These are orthogonal. Perpendicular. And what's, let's see. I can draw them, of course, and see that. 1, 1 will go, here's, if this is 1, it'll go here. And 1, so that's 1, 1. And 1 minus 1 will go there, it will go down. This will be the other one. 1 minus 1, so there's y1, there's y2, and they are perpendicular. But, of course, I don't draw pictures all the time. How do I test? What's the test for two vectors being orthogonal? The dot product. The dot product, the inner product. Y transpose, y1 transpose, y2. Or do you prefer to write it as y1 with a dot, y2? This is maybe better because it's matrix notation. And the point is, orthogonal, the dot product is 0. Right, 0. Okay. So that's good. Very good, in fact. So here's a very important fact. Symmetric matrices have orthogonal eigenvectors. So eigenvectors, what I'm trying to say is eigenvectors and eigenvalues are like a new way to look at a matrix, a new way to see into it. And when the matrix is symmetric, what we see is perpendicular eigenvectors. And what comment do you have about the eigenvalues of this symmetric matrix? Remembering what was on the board for this anti-symmetric matrix. What was the point about that anti-symmetric matrix? Its eigenvalues were imaginary, actually, an I there. Okay, here's the opposite. What's the property of the eigenvalues for a symmetric matrix that you would just guess? They're real. They're real. Symmetric matrices are great because they have real eigenvalues and they have perpendicular eigenvectors. And actually, probably if a matrix has real eigenvalues and perpendicular eigenvectors, it's going to be symmetric. So symmetry is a great property, and it shows up in a great way in this real eigenvalue, real lambdas and orthogonal y's. Shows up perfectly in the eigen picture. And let's see, I was going to say, oh yeah, here's a handy little check on the eigenvalues to see if we got it right. Of course, we did. I mean, that's 1 and 3 we can get. But let me just show you two useful checks if you haven't seen eigenvalues before. If I add the eigenvalues, what do I get? 4. And I compare that with adding down the diagonal of the matrix, 2 and 2, 4. And that check always works. The sum of the eigenvalues matches the sum down the diagonal. So that's like, if you only had one, if you got all the eigenvalues but 1, that would tell you the last one, because the sum of the eigenvalues matches the sum down the diagonal. That's sort of, you have no clue where that comes from, but it's true. And another useful fact, if I multiply the eigenvalues, what do I get? 3. And now, where do you see a 3 over here? The determinant. 4 minus 1, 3. So can I just write those two facts with no idea of proof? The sum of the lambdas, I could write SUM. Sum of, this is for any matrix, the sum of the lambdas is equal to this, it's called the trace of the matrix. The trace of the matrix is the sum down the diagonal. And the product of the lambdas, the lambda 1 times lambda 2, is the determinant of the matrix. Or if I had 10 eigenvalues, I would multiply all 10 and I'd get the determinant. Okay. Okay, so that's some facts about eigenvalues. There's more, of course, in section 1.5 about how you would find eigenvalues and how you would use them. Yeah. So we've got, that's, of course, the key point, is how would we use them. Oh, let me say something more about that. How to use eigenvalues. Okay. Suppose I have this system of 1,000 differential equations. Okay. Linear, constant coefficients. Starts from some u of 0. Okay. All right. How do eigenvalues and eigenvectors help? Well, first I have to find them. That's the job. So suppose I find 1,000 eigenvalues and eigenvectors. A times eigenvector number I is eigenvalue number I times eigenvector number I. So these y1 to y1,000. So y1 to y1,000 are the eigenvectors. And each one has its own eigenvalue, lambda 1 to lambda 1,000. And now, if I did that work sort of like in advance, now I come to the differential equation. How could I use this? This is now going to be the most, the constant 3-step, it's 3 steps to use it. 3 steps to use these to get the answer. Okay. Ready for step 1. Step 1 is break U0 into eigenvectors. Split, separate, write, express U of 0 as a combination of eigenvectors. Now, step 2. What happens to each eigenvector? So this is where the differential equation starts from. This is the initial condition. 1,000 components of u at the start, and it's separated into 1,000 eigenvector pieces. Now, step 2 is watch each piece separately. So step 2 will be multiply, say, C1 by e to the lambda 1t, by its growth. This is following eigenvector number 1. And in general, I would multiply every one of the c's by e to those guys. So what would I have now? This is one piece of the start, and that gives me one piece of the finish. So the finish is, the answer is to add up the 1,000 pieces. And if you're with me, you see what those 1,000 pieces are. Here's a piece, some multiple of the first eigenvector. Now, if we only were working with that piece, we follow it in time by multiplying it by e to the lambda 1t, and what do we have at a later time? C1 e to the lambda 1t y1. That's what this piece has grown into that. And other pieces have grown into other things, and what about the last piece? So what is it that I have to add up? Tell me what to write here. C1000, whatever that, however much of eigenvector 1000 was in there. And then finally, I've never written left-handed before, e to the who? Lambda number 1000. Not 1000 itself, but its eigenvalue, 1000t. This is just splitting, this is constantly the method, the way to use eigenvalues and eigenvectors. Split the problem into the pieces that are eigenvectors. Watch each piece. Add up the pieces. Yeah, that's why eigenvectors are so important. Yeah.
That first step of expressing not.
Yes. Right.
Is there one unique representation?
Well, very good question. Let's see. Well, the first thing we have to know is that we do find 1,000 eigenvectors. And so my answer is going to be, for symmetric matrices, everything always works. For symmetric matrices, if size is 1,000, they have 1,000 eigenvectors, and next time we'll have a shot at some of these, what some of them are for these special matrices. So this method always works if I've got a full family of independent eigenvectors. If it's of size 1,000, you're right, exactly right, to see that this was the questionable step. If I haven't got 1,000 eigenvectors, I'm not going to be able to take that step. And it happens, I am sad to report, that some matrices haven't got enough eigenvectors. Some matrices, they get collapse. You know, this always happens in math somehow. 2 eigenvectors collapse into one, and the matrix is defective, like it's a loser. Okay, so now you have to, of course, the equation still has a solution. So there has to be something there. But the pure eigenvector method is not going to make it on those special matrices. I could write down one, but why should we give space to a loser? Okay, so, but what happens in that case? You might remember from differential equations, when 2 of these roots, these are like roots, these lambdas are like roots that you found in solving a differential equation. When two of them come together, that's when the danger is. When I have a double eigenvalue, then there's a high risk that I've only got one eigenvector. And I'll just put in this little thing what the other, so the e to the lambda 1t is fine, but if that y1 is like, if the lambda 1's in there twice, I need something new. And the new one, the new thing turns out to be t e to the lambda t. I don't know if anybody remembers. This was probably hammered back in differential equations, that if you had repeated something or other, then this, you didn't get pure e to the lambda t's, you got also a t to the lambda t. Anyway, that's the answer, that if we're short eigenvectors, and it can happen, but it won't for our good matrices. Okay, so Monday, I've got lots to do. Special eigenvalues and vectors, and then positive definite.